We are now going to look at the way in which we plot radio navigation information on a Mercator chart. Pilots frequently use radio bearing information from such ground-based aids as VOR, which we have mentioned earlier in the course, VDF, which stands for VHF direction finding, and NDBs, which are non-directional beacons which provide a signal to the ADF, automatic direction finders, in our aircraft. Radio waves can change direction in the vertical sense and can be the space wave, the sky wave, or the surface wave, but these differences are only in their vertical direction. Their lateral direction is a straight line in space. When this refracts around the Earth's surface to form the sky wave or surface wave, the path is a great circle. Suppose that the transmitter was at Moscow and the receiver was at Vancouver. You can see that the radio wave would take the direct path, which is the great circle. A rumline track exists between those 2 points, but it is not the path of the radio wave. This presents a problem for us because Mercator charts show great circles as curves and rumlines as straight lines. Let's put a radio transmitter here and the receiver here. Here is the great circle joining them. And if we zoom in on the part between the transmitter and the receiver, we get the radio path. When we straighten up the meridians and make them parallel in the Mercator projection, this is how the radio path appears. This is where the problem arises. The great circle track angle changes. Let's assume, for the sake of this example, that the convergency between the longitudes of the transmitter and the receiver is 4 degrees. If we consider the great circle track going southwest, it will leave Oxford on 240 degrees true and arrive at the aircraft on a track of 236 true. The radio wave in this example is actually a true bearing measured at the ground station, a QTE, so it leaves the aircraft on a bearing of 056 true and arrives at Oxford on a bearing of 060. So immediately there is a difficulty. We do not have bent plotting rulers which can follow the path of the great circle track. Our protractors and rulers are straight. They don't follow the curve of a great circle. So we have to plot a straight line on the chart. But which straight line? If this is a QTE, the ground station measures an incoming radio wave from 240 degrees true and passes this information back to the aircraft. The crew have to plot from the ground station on the chart. They can't plot from the aircraft. They don't know where it is. That's why they're plotting a bearing. But if they put their protractor on the ground station and plot a straight line along a bearing of 240, it comes out here, north of the true position. If they could measure the radio wave coming from the ground station with their ADF, they would get a bearing of 056. Plotting the reciprocal, 236, remember you have to plot from the ground station, would give them a bearing here, south of their true position. The solution is to convert the great circle bearing into a rumline. Let's have a look at a practical example. An aircraft receives a QTE from Oxford Air Traffic Control of 240 degrees true. What bearing could be plotted from Oxford on a Mercator chart? Convergency between the aircraft and Oxford is 4 degrees. Convergency is 4 degrees. As you will recall, conversion angle is the difference between the great circle and rumline initial track and is half convergency. so conversion angle is 2 degrees. The rhumb line is always nearer the equator. In this example, the great circle bearing is 240 degrees true. Measuring clockwise, a line nearer the equator makes a smaller angle. So the rhumb line bearing will be 238. We now put our protractor over Oxford on the chart and plot the straight line bearing of 238 degrees true. The last example was of a bearing measured at the ground station. It was a QTE. VORs are also measured at the ground station. You read the information in the aircraft, but the bearing signal was modulated at the ground station. What if the bearing had been measured at the aircraft? Suppose we replace the VDF station with an NDB and put an ADF in the aircraft. In this example, we will measure a true bearing of 056 degrees from the aircraft to the NDB. We'll ignore at the present time any complications of magnetic variation or relative bearings. In this case, we apply the conversion angle at the aircraft end. As before, it's 2 degrees. This makes the rhumb line bearing from aircraft to NDB 058 degrees. Again, we're measuring clockwise and the rhumb line is nearer to the equator. But again, we're going to put our protractor over Oxford NDB on the chart and plot the rhumb line bearing from the NDB to the aircraft. Add 180 to 058 to get a bearing to plot of 238 degrees. It is essential to apply conversion angle at the end at which the bearing is measured. For a VOR or VDF, the bearing is measured at the ground station, so the conversion angle is applied at this end. A bearing of 240 becomes 238. For the NDB-ADF combination, or for airborne weather radar, the bearing is measured at the aircraft, so the conversion angle is applied here. A bearing of 056 becomes 058. However, as it has been measured at the aircraft, the rhumb line bearing needs to be reciprocated in order to plot from the ground station, which is on the chart. Let's sum this up. When propagated round the Earth, radio waves can change their vertical direction in space, but not their lateral direction. This means that, when refracted round the Earth, radio waves follow great circle paths. A rhumb line can also be plotted, but it is not the radio path. However, Mercator charts show great circles as curves and rhumb lines as straight lines. We don't have bent protractors or rulers, so we have to plot the straight line, which is the rhumb line bearing. We therefore have to apply conversion angle to the great circle bearing to get the rhumb line. Depending on the navigation aid being used, the radio bearing may be measured either at the aircraft or the ground station. These are the rules for applying conversion angle and plotting the rhumb line. For bearings measured at the ground station, that is, VDF or VOR, first apply magnetic variation at the ground station if necessary. Then apply the conversion angle at the ground station end. Then plot the rhumb line from the ground station. For bearings measured at the aircraft, that is ADF or airborne weather radar, apply magnetic variation at the aircraft and heading to correct for relative bearing if required in order to obtain a true bearing from aircraft to ground. Apply the conversion angle at the aircraft end. Reciprocate. Plot the reciprocal from the ground station.